Good morning. Today we're going to be discussing orbital fields, and they are at the basis of everything that I've learned and know about physics, the universe, computer science. Everything boils down to the truth about orbital fields. They are my version of Schrodinger's wave function, only mine is deterministic. And there's such a huge power that comes from having a deterministic view of the universe. Nothing is unknown. There is no probability functions that don't exist except in probabilities. Everything's a particle. Everything exists and is, deterministic. And I'm going to have to go back and cover a few of the things that I've already covered just to make sure you're clear on them. But at the end of this, orbital fields are the basis of NP complete, of the wave function, and they explain physics and every other branch of science perfectly. It really is, NP complete. So let's get started. Field theory, Euclidean space, three-dimensional space. If you look at space in this way, you can gain no knowledge except that space exists. They have literally taken this to the final degree of everything you can know. You can follow, you can track a particle's motion, you can define acceleration and deceleration or its momentum, and that's about it. You lose your ability to do anything after that. And that's why we have things like vector spaces, and we define things as divergence and curl. We have Minkowski space, and there's like 10 different spaces now. But they're all versions of vector space. They all work in the same basic fashion, and that's flawed. Space should be measured as fields from a core outward. If you don't do it that way, you end up with fields that permeate all of space, that must apply to every particle everywhere equally all the time, and then you lose your ability to build models separately that function and then put them together into a system. So Euclidean space, 3 dimensions. Everyone understands that. 6-dimensional vectors, simply add 3 more to the 3 you had. In order to fully surround all 6-dimensional vectors requires 8 cubic spaces. Once you install the 8 cubic spaces around the 6-dimensional vectors, between those spaces you get transitional planes. These transitional planes, when you name them in a field around a core radiating outward, and all fields start with a core and radiate outward. There are no fields that permeate all of space equally. And when you start to name them, when you start to discover physics, then what you get is, if you have a particle down on the page, right, what you get is, a surface of density. And in physics, modern physics even, it's considered kinetic energy and potential energy. And I say it gives 4 outputs, but it's still a plane of density. You'll see epsilon naught above, mu naught below, and this is where we begin to separate from modern science. You get 2 more transitional planes. You have 3 if this one is the plane of density. Then you have two more going this way and this way. And we call those the transitional plane of charge, negative and positive, and the transitional plane of polarity, monopole, dipole. I say that all fields radiate from a core, and in this case, this is a Planck core. That's it. H is Planck. So you have a bunch of very small, very dense particles that make up a core, and these are meant to be what de Broglie's standing pilot waves, and he calls them pilot waves, I call them standing pilot waves, but these are force out, charge in, and then behind the particle, force in, charge out, creating, right, on top of this plane of density, because of the kinetic and potential energy, 4 outputs, and we call those polarity and charge. Now, it's caused by displacement, right, and charge moving in and out. And when displacement and charge opposing each other create, well, again, de Broglie called them pilot waves. I call them standing pilot waves, but they are rotations around the cores. And you'll see that there's 4 of them in this picture. And these are the orbital dimensional vectors. In other words, you have 6-dimensional vectors originally, and because you get the 3 transitional planes on the plane of density, you get 4 more orbiting, right? One going one way, one going the other way, one going this way, and the other one going this way. They are opposing each other, and they are 4 additional orbital vectors. Okay? You have 6 straight dimensional vectors, right? And now you have 4 more orbital dimensional vectors. That gives us 10 dimensions in our system, without the entire system being accelerated or decelerated, which would be the 11th. And since it can be accelerated, which would be 1 dimension, or decelerated, which would be another dimension, you end up with 12 dimensional vectors possible. Only 11 can apply to any system at a given time. That's it. Very simple. Hopefully you can all follow it. If not, read the book, go back and look at some of the other videos. Now I'm going to move ahead here. And the reason that I'm going to move ahead is because those orbital dimensional vectors create what is called de Broglie's waves, or pilot waves, which I call standing pilot waves. These are the small epsilon naught and mu naught cores right here. And when you put 2 together, they act as gears. You can see that there's little arrows going above and below. And what happens is, when a particle leaves a core, right, it follows a helical path. And so the first quarter, if you were to leave the core, like this, or this core, right, if you were going to move outward, and it's a little easier to see over here, a particle would have to go up and above this core. But this epsilon naught positive charge is moving into the page, which means not only would the particle go up, it would go in. And this mu naught negative charge is coming out of the page. So when it gets, this one's rotating this way, this one's rotating this way. And if you follow the particle, it would go up and into the page, but then it would run into this one in between, and it would be pulled down and back out. And this would create a helix. Then it would be pulled under and back up, and you'll see after this there's another epsilon naught. So these standing pilot waves actually act like small gears that move particles through the system in a helical path. And that's what this is. T2 is the amount of time it takes to follow this path outward from the core, right? And Q1 phase is the first quadrant where it goes up and over that first, right? That first gear, this little tiny gear here, it has to go up, and when it reaches the point at the top, it passes the transitional plane of polarity, right? It passes this transitional plane, which is sideways here. And it goes from a, right? So the particle, when it first leaves, would be a charged dipole. Why? Well, let's look back here. Okay? It's in front of the core, so it's a dipole, and it's negatively charged here. Okay? So you have a negatively charged dipole. Okay? And then when it passes that transitional plane, again, it goes from dipole to monopole, but it still has this negative charge. So it goes from a charged dipole, right, to a charged monopole. That's it. So Q1 phase, leaving the core moving outward, would be a charged dipole. When you pass the transitional plane, right, from the core, moving outward, when you pass the transitional plane of polarity, becomes a monopole. So you have a charge monopole. Well, Q1 phase, charged dipole. Q2 phase, charged monopole. But then it goes below the plane of density, right? This plane of density with epsilon naught above, mu naught below. As it passes the plane of density, it goes to Q3 in our helix here. And the Q3 phase then switches from a charge monopole. It's still behind the core, so it's a monopole, but it becomes a magnetic monopole in Q3 phase. And then it gets pulled under, transitions again, coming back, passes the plane of polarity, and it becomes a dipole, which then, if you follow the helix, Q4 phase becomes a magnetic dipole. And then here's the thing, you're back at the plane of density, and when it passes the plane of density, it becomes a charged dipole. So you go from charged dipole to charged monopole to magnetic dipole, then back to Q1 phase. I mean, you're farther out from the core, but the helix repeats itself. So you're back to charged dipole. This is the overview of everything we're going to talk about today. And this repeats. When you have a core and it's moving outward in this helical path, the helix is getting larger and larger and larger. And in the end, you're going to find that what they call the strong force is this helical path following outward. Why would that be? Well, if you consider that the strong force is what we consider holding systems together, it's short in length, but very strong, hence the name strong force, which means when you radiate from the core, the farther out you get, the weaker it becomes. But it also is deteriorating the velocity of the core. So the V naught of the core is deteriorated by creating this helix over these standing pilot waves that de Broglie defined, and that gives us this outward force. And this strong force, this outward force going over, creating baryonic matter that's getting larger and larger and larger as it moves out. Technically, one side of this, if you exploded it out like a bell, this would look like exactly like what they say the Big Bang is, right? So this from here to here is the Big Bang. If you put just their little bell around it, you can see galaxies and universes and planets and stars out here. And from the core, they get smaller and smaller and smaller until you get all the way back to the Big Bang. Well, and I need to do a video on this, but for now, the Big Bang is this path from the core. And everything in creation is created along this path, over and under, as they transition through all of the different phases outward from this core. So you have a Planck core that's very dense, and when one of these chemtron particles, dark matter, gets slightly pushed in, the buoyancy pushes it back out, and when it comes out with a dipole charge. And that dipole charge is an inverted antipole, because this entire model is an antipole. So it comes out with a dipole charge, and that's your first particle. And it's what gives it mass and creates baryonic matter. That's how baryonic matter forms. You're going to see that the cores, which is what's shown back here, as they begin to radiate outward, two standing pilot waves create a torus, which, I can find it here, creates these orbiting dimensional vectors. The thing is, those orbiting dimensional vectors have a core and a direction that they're orbiting. And so they create a torus, and those toruses look like this. So two of these standing pilot waves create circling toruses that look like this. And you'll notice that the core is H, or, it's a Planck core. And that the core of the orbiting toruses are H bar, the reduced Planck constant. And that's because you're squaring H, which means instead of the plane being straight down that you're looking at, it's now orbital around the core. And they have velocity, which is why we call them dimensional vectors. These cores, H bar cores, have dimensional vectors around the particle, the core, the Planck core, the H Planck cores. And they create these toruses that then layer themselves, and those layers are actually, you're going to find out, also have helical paths coming out from them. And that's what we call the weak force. So the strong force deteriorates the V naught of the primary core, the Planck core, the H cores, and the weak force deteriorates, the orbital cores of the toruses. So the weak force deteriorates the V naught of the orbital dimensional vectors, where the strong force deteriorates the V naught of the primary H cores, Planck cores. So what I want to show you today is where each of modern science's great masters exist within this orbital field, and why I think it's such an amazing tool that allows you to understand all of physics and all of computer science. The reason that I'm so sure is because this Q1, Q2, Q3, Q4 output, is Maxwell's equations. And Maxwell's equations each represent a particle. Two of them are wave functions, and there's a 90-degree connection, an orthogonal connection, a symmetry between them that Maxwell found. Maxwell didn't actually write any of Maxwell's equations. He found an orthogonal connection between Q3 and Q4 particles, and that's why they're called Maxwell's equations. But what I'm telling you is that there is a 90-degree orthogonal connection between all of Maxwell's equations. So Q2 is charge monopole, and that's Gauss. Q3 is magnetic monopole, and that's Gauss. Q4 is either Ampere or Faraday, but each one represents an actual particle as the output to the orbital field that I'm defining. So when someone wonders how I'm so confident about everything that I'm saying, it's because I've built an orbital field whose output from the core is Maxwell's equations and calls them particles. And all that means is that when you look at any system, there will only be 4 types of particles. There will be charge dipoles, charge monopoles, magnetic monopoles, magnetic dipoles, and then it repeats. Let's take a minute and see what that would look like in our solar system and then here on Earth, just so we're clear. When you look at the solar system and there's only 4 particles, I say, then you have to ask which, define where each particle is, and what we see should line up with what I'm telling you. You have the charge monopole, obviously the star, and then there are only 3 other particles, right? There are no other stars, so we've found the charge monopole. That leaves magnetic monopole, charge dipole, and magnetic dipole. When you look at and know these systems, the final model of magnetic dipoles is an antipole. This is an antipole. And when you look at it, the first thing that should jump out at you is this little interior structure. And you can see the way it forms, right? Electric dipole, this would be our star, and it's a dipole because it has motion, right? So it's a charge monopole, but it's traveling through space, which gives it a dipole charge. So you have an electric dipole, and inherent to that, because you're in a galaxy, you get a toroidal dipole that it's traveling through. And so you get the electric dipole plus the toroidal dipole that can create an antipole. The antipole, this is our galaxy, this is the toroidal dipole, and when you add the toroidal dipole to the electric dipole field, you end up with the antipole structure, and that antipole structure fits Jupiter perfectly. Now, if you don't believe that, that's fine, but let's set aside what particle it represents on our solar system for a second and realize that I've come to the conclusion through my orbital field that when you invert the antipole, this moon-making structure moves to the outside of a particle, right, and creates what science calls a quasi-particle, which is simply a space, like a electron hole where an electron can fill. So you have this moon-making structure inside or outside a particle. Those are the only 2 options. It's not like you can say, well, there isn't if there isn't this moon-making structure, then it's either a charge monopole or a magnetic monopole. So since there's only 4 particles, then this moon-making interior structure, right, created by, and this is not in question. Science knows that an electric dipole plus a toroidal dipole makes an antipole, and that the antipole is modeled like this. Right? None of this is in question. The only question is how you're interpreting it. And since I call this magnetic dipole, then if you invert that antipole, right, the final model in the magnetic dipole is an antipole. If you invert the antipole, this moon-making structure flips to the outside. And it does that when you flip, right? Our original core had force out in front of it, charge in, and then behind it has charge in, force out. So all we're doing to flip this charge is to flip the force and charge. Right? So inside, or a antipole, you have a force out, charge in system. And around a charge dipole, you have a charge out, force in system. Now that we've defined how the forces should be and where the moon-making structures are, let's just go back and look at our solar system. if you look at the inner planets, they have no moon inside their structure. Right? That's obvious. The moons are outside. So just logically, use your intelligence. Where would the moon be? Right? It's outside Earth. It's orbiting it. It's outside Mars. It's orbiting it. It's outside the system. Now, some people will say, well, it's outside Jupiter too. Well, they get to the outside. But then they're their own charged dipoles. This system is of a particle with an internal moon. So what would that look like? Well, look at Jupiter. You see the red spot on Jupiter. It's been there ever since we could see the planet. What causes that? It's an interior moon that's forming, and when it gains enough velocity, its momentum will carry it outside the atmosphere of Jupiter, and it will birth a moon. That's it. You can see a moon forming from Earth. You don't even need to go to space to test it. So, if you're going to look at the outer planets and the inner planets, the anipoles, the magnetic dipoles, are obviously the outer planets. There is no possible way a moon forms in the atmosphere of Earth or Mars or Venus. They form outside. Right? So the only model that shows a moon forming outside in this quasi-particle, in this space, is around a charged dipole. So the inner planets, Venus, Earth, Mars, must be charged dipoles. And the outer planets, Jupiter, Saturn, Uranus, Neptune, must be anipoles, magnetic dipoles. And that only leaves magnetic monopoles. And if you look at the model, right, an anipole, the interior moon here, will birth charged dipoles. Okay? So look at our moon. Is it a charged dipole? No. Well, the only other model that can exist based on Maxwell's equations from a core, right? All four particles in a helical path from a core that then repeat, is magnetic monopole, which means the moons of the inner planets must be magnetic monopoles. Period. It's not a guess. I'm not, hey, I got a crazy idea that might be. It is an absolute certainty. They must exist in this place. The outer moons are charged dipoles that are created in here and then pushed outward. And the moons of the inner solar system are magnetic monopoles around charged dipoles, which are inverted anipoles. So, where in all of this, this is the way we look at the solar system. Now, and I understand this is new to a lot of people, and it's going to freak some people out. So the question is, what evidence would there be against this right off the bat? And that, of course, the tides of Earth. Well, okay, let's talk about those. They're in another video too, but let's just hit them real quick. If I've said that the only four particles that exist in the universe, in all of creation, are charged dipoles, charged monopoles, magnetic monopoles, and magnetic dipoles from a core, Q1, Q2, Q3, Q4, going over and under de Broglie's pilot waves, standing pilot waves, right? Creating these quadrants, and that they are Maxwell's equations, and that each of Maxwell's equations represent a particle, and that every particle in Maxwell's equations has a 90-degree orthogonal connection. Where he found one, there are three more. I've explained them. They're simple. Let's look at all the other things on Earth, and let's assign one of the four particle types to each of the things that we see happening, so that I can prove to you, hopefully, that what you're seeing is also charged monopole or charged dipole, charged monopole, magnetic dipole. Now, H2O, water, if you invert this antipole around a particle, right? You have a dipole, which is a north pole and a south pole put together, which is, you have to have two of them. So H2O, hydrogen 2, oxygen 1. One oxygen atom with a dipole hydrogen around it would create charged dipoles. If our moon's a magnetic monopole, it's a negatively charged object traveling through positive space, and if that's the case, the helical path it's making when it travels is a solenoid, which is creating a magnetic field, not on the moon, but between Earth and the moon. And that means that if H2O is a charged dipole, it would be moving toward the core of the magnetic field created by the solenoid, which is our magnetic monopole moon traveling in a helical path through space. So the tides of Earth don't dissuade me or the model in any way. They fit perfectly, in fact. In fact, it fits better than a gravitational model, because gravitational model says that those charged dipoles should be trying to reach the moon itself. And they don't. They try to reach a point in space behind the moon, trailing the moon. The core of the magnetic field created by the solenoid of the magnetic monopole moon traveling in a helical path through space. But let's keep going. I've already mentioned that. It should be old news by now. What other things can we see on Earth that would make sense? In other words, let's apply the same logic to the particles here on Earth we see. Well, there's a bulge on the backside of the moon as well, and that's created partially by the magnetic field, right? Goes out in both directions and rotates back. So you're going to get some of that from the magnetic field, the field lines from the magnetic field created by the moon. You get the idea. But what about molecular oxygen in the air? When you breathe oxygen, you don't breathe atomic oxygen, single atoms of oxygen. They're dipole oxygens. It's dioxide, really. It's two oxygen atoms. Well, those are magnetic dipoles. So what would that mean to Earth? How would we know that? And the answer to that is pretty clear. The charge monopole of the star attracts magnetic monopoles or dipoles. So the magnetic dipole oxygen of our atmosphere wells up on the side toward the sun. It stretches out, it bulges out our atmosphere, not the water, toward the sun. And the weight of all of that lifting as it tries to go toward the sun creates a valley underneath of pressure where it allows the charged dipoles of water to rise up. The weight of the atmosphere is actually significant, and you're gonna feel it. And when the magnetic dipoles of oxygen that we're breathing are lifted, they lift toward the sun as it passes, just like the charged dipoles lift toward the core of the magnetic field created by the moon. And this is the basis of weather. I mean, yes, the heat from the star heats air that makes it rise, but that's not what we're talking about. We're talking about static charge of every magnetic dipole. Let me prove this to you. Breathe in. Right? What happens? I'm saying that oxygen is a magnetic dipole. The final model in the magnetic dipole is an antipole with this little moon-making structure, and that Jupiter is also one. So let's look at Jupiter as a magnetic dipole, and all of the material that comets, asteroids that hit it, with the force out, charge in system, build up and get pushed back out into this moon-making structure, and are held there until they create until enough energy is added that they gain momentum and get pushed to the outside of its atmosphere. Okay, so I'm saying that when you breathe, you're breathing in dioxide, right? Molecular oxygen, which is, I'm saying, an antipole, which is this same structure. So when you look at Jupiter, it's a dioxide. I mean, it doesn't have to be oxygen, but it is a dipole, a magnetic dipole. Molecular oxygen in the atmosphere is too. So let's look at our respiratory system. Plain and simple. Let's prove it. You breathe in. What happens? Not only when you breathe in do you pull the oxygen in, right? But your lungs expand. And when they expand this antipole slightly. And when they do, it pulls a carbon atom into this interior moon-making structure, and your dioxide that you breathe becomes carbon dioxide. That's it. This is how your respiratory, and all breathing animals really work. Even fish underwater. Charge dipoles are passing through in the form of water. They're carrying small, compressed, magnetic dipoles with them. And when the gills pull, they not only pull the water through, they expand those dioxide molecules, and they absorb a piece of carbon in the gills from the fish. They expand in your lungs, and when they expand, they pull, right? Just like an asteroid or a comet hits this and then builds up in here. When you expand the dipole, it pulls a carbon atom in, and it becomes carbon dioxide. So let's keep going. You breathe out, the carbon in the antipole dioxide gets pushed back out, and then it goes and runs into a plant's leaf somewhere. So I'm saying that when this moon births, when you apply energy to it and it builds up its momentum, it moves outside, right? So what happens in photosynthesis? What happens in that leaf? Well, 9 photons, it's been measured, it's scientifically known, you can disagree with me if you want, but 9 photons of energy. These are magnetic monopoles carrying energy, but we're getting beyond that now. When you apply 9 photons of energy to a carbon dioxide, what happens? Well, the energy increases the momentum of the carbon atom inside and moves it outside the atmosphere, making it dioxide again. So how do you breathe? Well, it's the antipole, and it's still one of Maxwell's 4 particles, defined by Maxwell's equations. It's our respiratory system. It's how we breathe. It's how the tides form. The bulge of the water is static charge. All of these things are better defined with my model, with orbital fields that have the output of Maxwell's equations, that are particles, and these are the only 4 particles in existence. So, molecular oxygen is an antipole. Water is charged dipoles. Photons, magnetic monopoles. And when you realize that this is what's happening, that every single system that you call gravity and all these other things, or that you say gravity is causing, you can better define them when you do it as 4 possible particles: charged dipole, charged monopole, magnetic dipole. And in case you're still wondering, this sounds a little hinky or whatever, think about how a dog or any animal chases you by smell. If the smell just hung in the air, it would dissipate. They wouldn't be able to track you. How can an animal track you by smell the way that they do? Well, because the smell is held inside the dioxide on the carbon atom inside this moon-making structure. And when they breathe in their nose, again, their nose not only pulls the air in, it expands it slightly, and it moves this moon, right, this interior quasi-particle, whatever you want to call it, outside. There's only two ways to get the carbon atom out of carbon dioxide. You either have to accelerate the interior moon, the carbon atom, to move it to the outside, which takes 9 photons of energy. We already know that. Or you have to expand the antipole, which allows it to be pulled out. In other words, you reduce the resistance or you increase the energy. That's all I'm saying. But how does a dog or something else follow you with smell? Well, your smell can be carried miles away in these dioxide, but it maintains its smell, its potency, because it's maintained in the carbon atom that's maintained inside the antipole of the dioxide. So every single system, right, when you go back and you start rebuilding the elementary chart, right, you need to do it with charged dipoles, charged monopoles, magnetic dipoles. And you will see that every one of them is better defined when you have 4 kinds of atoms, when you have 4 kinds of molecules, when you have 4 kinds of planetary or, solar system size structures. And that everything in existence is one of those 4, period. The universe is an antipole. The galaxy is a toroidal vortex, right? The solar system is a charge monopole, right? So there is nothing that cannot be defined better as Maxwell's equations as particles, and those 4 particles define every single interaction better than any other model. The reason that I am absolutely sure that this model is real and that it works is because no matter what system I apply it to, it absolutely solves all my questions almost immediately. And there's a few that it took me a little longer to understand, but it solves atomic problems, molecular problems, solar system problems, subatomic particles. It solves how dark matter becomes baryonic matter when the antipole inverts around a chemtron structure, around dark matter, to give it mass and charge. And again, let's go back and look at where the great masters exist in this. Okay? De Broglie's waves around Planck cores. So we found de Broglie. We know where he exists, where his particles exist. Right? It's the surface of this water. It's the surface here of this core. And you have to ask, who else can this define? Right? Well, it's kinetic and potential energy. If you've ever looked at the actual Lagrangian equations, and not everyone has, but if you've actually looked at them, they are discussing the kinetic and potential energy. Well, that's the kinetic energy of the particle against the potential energy of the system that it's going through, and that creates this surface, this plane of density. So what we're talking about is the Lagrangian. But at the same time, it's the Hamiltonian, which again is kinetic and potential energy of the system. So what we're talking about along this plane of density defines the Lagrangian, and it defines the Hamiltonian as a model, not as an equation. See, and that's the difference between me and other people who have tried to define this for you. They come at you with equations, and I have no problem with equations. Except, in my mind, I don't see the equations. I don't see the numbers. I see models. When you show me equations, I see them as models, not numbers. It's like you have no idea what your numbers actually mean. You just create the numbers. Well, this times this divided by that, extrapolated through, comes out to be this, and that means, since we've seen that number again over here, then it must mean, right? And I get it, but you have no models. So then you go back after you have the numbers and try and build models, but your models don't fully extract the knowledge in your equations. And all I'm trying to do, I'm not trying to change your math. I'm using the math of de Broglie. I'm using the math of Bohm. I'm using the math of Lagrange and Cantor, Dirac. All of these people, I haven't changed their equations. I'm not arguing with the math. I'm 1,000% positive that they're right about the math. So, you get these physicists who are all, just, go do the math. Well, the math is done. It's been done. I'm using your math, or actually the math that you memorized from these great masters. De Broglie's waves are on the surface of this plane of density. Bohm's too. And all I'm saying is that the model that you use to define your equations are incorrect. You're exceptional mathematicians, but you're crap at modeling. I'm sorry, it's the truth. Your models don't keep up with your mathematics. And all I'm trying to do is solve that. So don't tell me to go do the math. The math is done. It's my point to tell you to go do the modeling, to refix your models because they don't work. The output on this surface, right? You have a single particle, a unitary particle, going through, creating a plane of density, right? A binary system. And that plane of density has quad outputs, which you see here. And when you label them, right, as polarity and charge, based on displacement and the flow of charge, displacement of particles, which then displace charge, you get 4 outputs, and those 4 outputs create these accelerated dimensional vectors orbiting it. You have 6-dimensional vectors that create 8 cubic spaces, which create 3 transitional planes, which then define everything in existence. When you follow those, you then get 4 more orbiting the core, and those are also dimensional vectors. And those 4, right, are what Einstein is talking about. What does that mean? Well, I guess this is about the best one. 2 de Broglie's standing pilot waves, which he called them pilot waves. I had to add standing because they are standing pilot waves, create a torus. Einstein's time is accelerated cores. So when I say, when M theory requires, an 11th dimension, which is Einstein's time, they're saying that their 11th dimension is equal to Einstein's time, right? And I'm saying that these cores, right, these orbital dimensional vectors, right, they have a vector, and they are cores, and they create a torus, and Einstein's field equations and his mathematics are defining those toruses, 4 of them in every system, and that the accelerated cores are his time, and that the curved space and time of Einstein is simply and exactly in these toruses. If you look at a torus, on any point, it is a complex curve. And I mean, it curves this way and it curves this way. And there is absolutely curved space at every point in a torus. And the cores are accelerated. You have accelerated curved space. This is Einstein's field equation. They're about the toruses. That's it. So where is Einstein? Am I disagreeing with Einstein? Absolutely not. I agree with his mathematics. But again, you've put his mathematics in the wrong place in the model. See, the problem is when someone creates something, it is the natural assumption to just say, oh, Einstein discovered space-time. It must be equal everywhere. Space-time is the answer. And before him, it was Newton. Newton discovered gravity. They did all their math in the atmosphere of Earth, where gravitational model exists, and then into space around us. But again, that's the gravitational field of the sun, the atmosphere of the sun. So gravity is only as far, gravity is, plain and simple, if I can find it here, caused by this inverted antipole. The gravity of Earth and any charged dipole is the inverted antipole, creating a force-in, charge-out system. Gravity is a local force. Space-time curved is a local force within... Jesus, I can't find all these things, and I want to. Within these models. There. Space-time exists within the curved, accelerated space caused by the toruses orbiting the core. Two of those toruses on top of each other create a toroidal vortex, which creates the galaxy. And four of them, right? So this is our galaxy. This would be a charged dipole. This would be an outer solar system moon, an inner solar system planet, and this would be an antipole. So this would be a universe. This would be an electron. This would be dioxide from the atmosphere, and each one of these is a different form. There are 4 orbital dimensions, and they are in the form of toruses. So you want to see Einstein's 4 orbital dimensions on Earth. In other words, let's not do something so small like quantum mechanics that you can't see. I'm saying that, a charged dipole like a proton would have this structure, right? So how can I explain it to you in a way that you can see all 11 dimensions, or the 10 dimensions that you can see, plus the acceleration of this whole particle, which would be the 11th. This is 10 dimensions. Well, if I'm saying a proton is a charged dipole, and it is, and I'm saying planet Earth is a charged dipole, and it is, then planet Earth should have these 11 dimensions. So let's look at them. Where are they? You've got the 6 dimensions, north, south, east, west, the 4 going out in all directions, and the 2 going, above and below. That's 6. No one's going to argue with that, I think. Where are these 4? Well, you've heard of the trade winds, haven't you? Trade winds orbit. Remember, these are dimensional vectors, which means they are orbiting. One is orbiting one way, one is orbiting the other way. And if you look at our planet, it has trade winds. They're weather patterns orbiting the planet. So what are these small ones on top? More trade winds? Well, we call them polar vortexes. So all 10 dimensions of physical space, right, around planet Earth Trade winds, polar vortexes around the 6 structural dimensions of the particle. And they're the same thing around a proton, because it's a charged dipole. Or there will be the same things around the moons in the outer solar system, because they're charged dipoles. Anything that's a charged dipole, right? Carbon atom will have them too. Why? Charged dipoles. If these are the polar vortexes and these are the trade winds and they fight each other, right? Last winter was an extremely cold winter in the north and in the United States, right? Very, very cold. Big storms. And when you listen to the weather people, what do they say? Well, the polar vortex pushes down and pushes the trade winds, which cause this cold weather to infiltrate lower than it normally does. So, see this? See how these on top have pushed down and pushed these outward? What happens on Snowball Earth? What happens when, we get an ice age? Well, these polar vortexes are pushed down underneath, right, these trade winds. So the trade winds move outward, are stretched outward, and the polar vortex moves down inside. And that carries the cold weather down around the planet and up around the planet on the bottom, so that you can cover the whole Earth. So when the pressure of the polar vortexes, which are these dimensional vectors, push down and up from the bottom, they move the trade winds, right, outwards, and you get ice ages. If you want to study Einstein's curved space and time, well, their polar vortexes and the trade winds here on Earth are 4-dimensional vectors that are curved, orbital dimensional vectors. And those orbital dimensional vectors are toruses. And all of the toruses in the orbital dimensional vectors of every particle, from as small as they get to as large as they get, are what Einstein's field equations are talking about, and what curved space and time really is. So this is Earth. This is a proton, right? This is a carbon atom. This is the inner planets, or the outer solar system moons. These are toroidal vortexes. This is what this looks like when you take away all of the stuff and just look at the orbital dimensional vectors. This is what it looks like. This is what your galaxy, this is what causes your galaxy to form. And this is your universe. This is what your universe is going to look like when you zoom out and look back in. This is the 10 dimensions, 6 regular dimensions, 4 orbital dimensions of your universe, and of Jupiter, and of dioxide molecules, oxygen molecules in the atmosphere, and electrons. They're all antipoles, and they all have this structure. Toroidal vortexes, right? Galaxies, right? They're all going to have 6 regular dimensions, 4 orbital dimensional vectors. Charged dipoles, right? They're going to have 10 dimensions, 6 regular dimensions, 4 orbital dimensional vectors. You can see them on Earth. If you want to argue with me, go ahead. But you can see the polar vortexes, you can see the trade winds, you can see all 10 dimensions of Earth, and it's a charged dipole, which means you can see the same things. Let's talk about, real quick, string theory. What do they say? When you look at things, when you break them down to their smallest things, even space, and you're looking at it, you can actually see little tiny lines created, right? Blue and red lines flickering in and out of space. Well, if these have a dimensional vector, right, and you zoom into a piece of dark matter, a piece of that's trying to gain charge and become baryonic matter, you would have these tiny orbital strings. See, I'm going to tell you what I think string theory is talking about, but you're going to have to ask them if it's what they really see, because I do not follow string theory math when it gets way out there. I'm not that much of a mathematician. But in my model, when I'm modeling something, I listen to what they say, and they say that if you zoom in, you see little tiny strings. Well, if I say that the inverted antipole structure gives it its mass and charge, and string theory says that mass is created by little tiny strings, then these orbital, right, dimensional vectors become those little tiny strings. And as the size of them and the frequency of them decides its mass and its charge. Well, if this is right, and it's an inverted antipole structure that gives it its charge and mass, which is what I'm saying, then these 4 orbital dimensional vectors are the strings around the particle that they're talking about. And some of them, like I say, they're reversed. So this one's moving this way, this one's moving this way, this one's moving this way, this one's moving that way. In redshift, we already know. If you look at, energy and it's moving away from you, it looks red. And if it's coming towards you, it's compressing, it looks blue. You would get little red and blue strings around particles because some are orbiting toward you and some are orbiting, away from you. Sounds like what they're talking about. Whether it is or not, you're going to have to ask them. I am not a string theorist. But if string theory is so correct, I know my model is correct. And if string theory is correct, and they say there's 10 dimensions, and that this would fit what they're saying. It's not perfect, but it's at least a start to where you can visualize everything you hear about string theory, add it to this model. Well, what else do we hear, right? Well, some strings are closed, these, and some strings are open-ended. And I don't mean open-ended to be the internal dimensions, right? When I say open, what would that look like? Well, to me, it looks like a small helix, almost like a little tornado, if you just drew it smaller, getting bigger and bigger and bigger. And what did I say about Jupiter? It's an antipole, and that the storm, right, the red dot on Jupiter, is actually a charged dipole moon that's going to birth. Well, the way that forms, it may look like this from here in a simple single model, but what that would look like inside the atmosphere would be a giant tornado. And if you just took that model, it would be an open-ended string, right? With each one would have a slightly different size and frequency, right? Different number of helixes and the size and frequency of those helixes would exactly match the size of the charged dipole being created inside the antipole. So strings, closed strings, and open strings, like little, these go around the surface, right? So the surface of the particle, if it's going around them, that's a closed string. And if you have this particle and the strings are coming out from it in a helical path like a tornado from the surface of Earth outward, that's an open-ended string. Each string slightly different. Each one is equal and opposite to the charge and mass of this particle, or the charged dipole here, which would be this particle. So in my mind, what I'm saying actually agrees perfectly with string theory. And since M theory is all of the string theories put together with an additional an additional dimensional vector, which is if these accelerated cores of these toruses orbiting are Einstein's time, right? If the accelerated cores, if the acceleration of those cores is Einstein's time, then acceleration and deceleration is the 11th dimension in M theory. This proves string theory, if that's what they're talking about. If it's not, just go on and, take what fits throughout the rest of life. But from my point of view, it proves string theory. It proves M theory, right? It proves Einstein, but only in certain areas. Only where these toruses exist. And these toruses are these dimensional vectors. And they have cores, and that there is layering around the cores, and those cores are accelerated in a certain way, giving them a vector, dimensional vectors. Einstein's math is correct. It only applies to the orbital toruses, the accelerated cores. And this is how they come out in the systems. So I'm telling you, I agree with Einstein, but I'm telling you where he exists in the system. And I agree with Newton, right? It's an inverted antipole. It's a local force from a particle outward. Gravity is not universal. The speed of light and Einstein's field equations are not universal. Curved space and time is not universal. It's within the toruses. It's around these dimensional vectors. That's it. So we don't have universal gravity. We don't have a universal speed limit on energy. And we don't have universal curved space-time. They all exist, but they are local. They're not universal. They're not everywhere equally. There is no field that permeates all of space equally. It just doesn't exist. So we found de Broglie, right? We found Einstein. We found Bohm. We have found string theory and M theory, where it would exist and where it wouldn't exist. We have found on the surface, right, the Hamiltonian and the Lagrangian. The four outputs are Dirac's equation, which there's another video on that. I'm not going to go into it too deeply, but it's, the four outputs are polarity and charge. Monopole, dipole, negative charge, positive charge. And we found Cantor because Cantor's ternary set, when you look at it from a particle physics viewpoint, is one, the other, neither, and both quadratic outputs in thirds. 0 thirds, 1 third, 2 thirds, 3 thirds. And I've shown you this in the other videos over and over, so I'm sure I have one here somewhere. 0 thirds, 1 third, 2 thirds, 3 thirds, Planck core, or a core of a field going straight down on the page creates a binary output. That binary output, right, is the plane of density above and below. And on that plane of density, right, this plane, you get quad outputs, which are monopole, dipole, negative charge, positive charge, no thirds, 1 thirds, 2 thirds, 3 thirds. So, Dirac's equation, sitting directly on this plane of density, I agree with Dirac. Cantor's ternary set defines it as 0 thirds, 1 third, 2 thirds, 3 thirds, which once you understand that charge is not equal, it's 1 third, 2 thirds, then monopole and dipole immediately become no thirds and 3 thirds. And so I'm agreeing absolutely with Dirac, Cantor, and Cantor's ternary set is what the Mandelbrot set is based on. And fractal geometry is based on Mandelbrot. So technically, we're agreeing with fractal geometry, and we're tying fractal geometry into Mandelbrot, which ties it directly into Cantor's ternary set, which ties it, according to me, directly into Dirac's equation, which sits which are the four outputs, right, to the plane of density. And it's that plane, that fight between kinetic and potential energy, that the Lagrangian and the Hamiltonian are defining. So I'm not changing anyone's math at all in any of my models. Every single one agrees. I'm just changing the model. The way the system works, I'm showing you. Building a new model for the current mathematics. That's it. De Broglie's waves orbiting, had to turn them to standing pilot waves, not just pilot waves. And all of this then defines the orbital field, and the orbital field has the outputs from the core outward here around a helix that are Maxwell's equations. So the output to the orbital field is Maxwell's equations. I'm agreeing with Cantor. I'm agreeing with Dirac. I'm agreeing with Einstein. I'm agreeing with de Broglie and Bohr, Bohm, and, Bohr too. When you build the model of the universe, I actually agree more with Bohr than you guys do. You guys have changed his model because it's just probabilities, but it's not. Which means his model of the solar system and Rutherford's as being closer to the inside of an atom is correct. So I am more agreeing with Bohr and Rutherford than you are in reality. But it's I'm agreeing with Gauss and Ampere and Faraday and Maxwell. I have not changed our mathematics in most cases. And where I do, it's, the divergence of the magnetic field equals 0. Well, it equals 1. It's real. The thing is I'm not disagreeing with Gauss. Gauss thought it was real. Gauss said it exists. I just can't find it. Right? So I'm not disagreeing with Gauss. I have literally built a model that proves all of the people you say, the great masters of physics. And the thing is I can go all the way back to Plato. He tried to build the entire universe out of Platonic solids. And I'm getting off course here because this is going to start making me sound like a crackpot, But if you look at an orbital field, the four outputs, are the square of the octahedron. And the point ahead of and behind that square is the density difference. So the orbital field is the octahedron. And tetrahedrons are eigenstates of any particle. You've got one above, one going this way, and one going this way. So tetrahedrons are the force profiles of particles, and the octahedron is the orbital field I'm talking about. And the square is the space and the magnitudes on all sides of the system. And I wrote it in the front here, so I'm going to read it real quick. It was the belief by many of the first intellectuals that the physicae could be defined by the square and the compass. Many great minds have debated the circle and the square. In this manuscript, I reveal that the sphere is created in the cube that is formed by the tetrahedron that is the result of the octahedron that forms from the layering of spheres. And all of that is true. And the only thing you need to add in order to model everything to his Platonic solids are the sphere, the helix, the torus. I think that's it. So he had 5 Platonic solids. You need 3 more. They're not Platonic solids, but if you add those 3, you end up being able to create with those shapes everything in existence. Everything is geometric. People ask, is math invented or discovered? Well, it's discovered because even number theory itself, right, which I have a thing on prime numbers, is 1/3 and 2/3 and is a geometric from a core outward. It is based on orbital fields. Everything in existence is based on orbital fields. And these orbital fields, which you call Schrodinger's wave function, has the probabilities inherent in it. So if every particle has the wave function, internal or external, that isn't a monopole, you can answer every question with orbital fields. And I'm going to show you how powerful this really is. And I hope that I don't lose some of you here. I solved the traveling salesman problem, and I did it using my orbital field. And I'm going to do a video on this, so I'm going to keep this very short when I show you. But you can see how 6-dimensional vectors create 8 quadrants of space and 3 transitional planes. And so what we want to know, what we want to prove, is how this would apply to something like the traveling salesman problem. Now, this orbital field is what I call NP-complete. And NP-complete, this is not a specific definition, but P equals NP shows, polynomial compared to non-deterministic polynomial. It gets complicated, but it creates levels of difficulty for problems so that you can rank them. And the basic theory is that either they're all within the same problem class and we just don't know how to solve them yet, or there are different problem classes and some are solvable and some aren't. Well, P equals NP says that they are all within the same class and they're all solvable if you know how to do it. And I know that that's true. So P equals NP, absolutely. But at the end of that is something called NP-complete. And what NP-complete really does is creates a model, a solution, what they hope is an algorithm, that when you apply any problem to it, it's like, think of it like languages. All these different languages. NP-complete would be a translator that translates, you ask a problem in this language and you can translate it to this new language where there's a solution, right? So NP-complete is the translator that turns all problems into one problem that you have a solution for, so all problems are solvable. And that's what this orbital field is. This is NP-complete. How do I know that? How can I prove that to you? Not only does it solve physics, it solves quantum mechanics, it solves every computer problem that there is. Every NP hard problem is solvable with this model. Every question in physics is solvable with this orbital field model. This is NP-complete. And I don't mean this is a solution that we might even, this is the translator that solves all problems. And I know what that sounds like, but it is. How do you think I can solve quantum computing? How can I solve quantum mechanics? How can I solve quantum gravity? How can I, tell you that the outer planets have an anti-gravity atmosphere and that, Jupiter is birthing moons and the red spot is a moon and that, water is charged dipoles and is moving to the magnetic field created by the moon. I have come up with so many new theories that I sound like a complete lunatic, a crackpot, right? And I just have to deal with that. Why am I so confident when everybody on the planet, not everybody, but, a great many people say, this guy's a lunatic. He must be. Well, I'm so confident, and I'm absolutely sure, because I have a model that is NP-complete. And no matter what problem I have ever thrown at it, it gives me a solution. This orbital field is NP-complete. So let me show you. how do you solve the traveling salesman problem? Well, first let's just, for those of you who haven't done it before, if you take any random area, right, and you put a town here, and a town here, and a town here, and a town here, and a town here, basically, you want to travel the shortest path between all of them, the most efficient way. Never visiting a town more than once, because that would be inefficient, and completing a loop of all of them, knowing that it's the shortest path. Now, there are solutions that are very close, but none that are perfect. I'm going to tell you how to build the perfect one. Right? There's only 3 things that you need. And just so you're aware, I don't mention it very often, but Rationis Physicae, this is the book that I wrote, and it's for sale on Amazon, and it's for free on the Kindle Amazon Reader. It's not about making money off of it. It's about sharing the knowledge with people. I think it's just so amazing that I want people to see the solutions here. So P equals NP, at the very beginning of the book, I do a prologue where I just say some things to open up the door to solving an NP hard problem to show you what we're dealing with. And then P equals NP, I'm going to prove it in the book by solving the traveling salesman problem. And you can see it's only 2 pages. So a lot of you thinking, you can't solve it like that. You can't solve it that fast. But you really can. And there's a reason you can solve it that fast. There are only 3 things that you need to know. How would that function? How do you use the orbital field that I just talked about, physics and quantum mechanics, and how it interacts with all of those things? How do you apply that to the traveling salesman problem? Well, and actually any of the NP hard problems, but let's just use this one for now. I'm going to switch back here. I like to show my models here. So, first of all, the traveling salesman problem can be solved on a flat 2-dimensional surface, but it's not as useful as one that's in 3 dimensions. So there are 6 possible dimensional vectors. So if there's towns above and below, like at the top of mountains and the bottom of valleys, you need to go up and down and outward, in the 2 dimensions. So we're going to solve it in 3 dimensions, not 2. And these are the 6 possible dimensional vectors. So what's different about how I solve it? Well, fields radiate from a core. So instead of, the problem with the traveling salesman problem is they can solve it for just a few cities easily. But when you have 1 million cities, it takes exponential amount of time to solve, thousands of years. So they have no, polynomial, which would solve it very quickly. So if something like this, they can solve in seconds. But if you add 10,000 cities, suddenly it takes years. So what we're going to do is, what's different about my algorithm, my model, than others? Well, I say fields radiate from a core. Okay? So we're not going to look at all of the cities, no matter how many there are. We're going to look at each city individually, and we're going to answer all questions about it by its own field. So how does that work? Well, it's how you keep it from being an exponential problem, from extrapolating exponentially. And the way you do that is every city has its own. So you can start on any one of these, and you don't need to know how many other cities there are. It's irrelevant. That's your problem. You're trying to apply it to every particle, and then apply it to every particle in a different way, and then apply it to every, in a different way. And this is where you run out of problem. This is where you run into problems. If you have a city, we don't care. This algorithm doesn't care how many cities are in it. Why would it? Every particle is its own. Once you understand each particle, you connect it to the one below it and the one above it, and it's how you come up with the accurate solution. So how would that work? Well, the first thing you want to know is the distance to the 6th particle. You measure the 6 closest particles along each of the 6 dimensional vectors. So when you build your algorithm, and I don't do computer programming, so I'm not going to put this on a computer, but you have to simply get the distance, measure the distance along to the nearest particle along each of the 6 dimensional vectors. So that's the first thing you need to do. Step 1. Step 2 is to create the space. And this is my idea that separates my model from all the other people who have solved the traveling salesman problem before. You have your space, right? Distance along each dimension. So the distance to the nearest city, up, down, left, right, forward, backward. Once you have that, the second piece of information you need is the space. And this is where it gets a little more complicated. But just like the 8 quadrants of space, every city will have 8 quadrants. Now, what you have to do, and this is the part that's, hard to program or harder, I've never done it, so, is you have to create a grid for all your cities. 2-dimensional, 3-dimensional, doesn't matter. And you create a grid that puts a square around each city where it falls inside of a square and is still the same, right? Oops. But once you create a grid, you adjust the squares until every city is within one of your squares or your cubes if you're doing it in 3 dimension. Once you've done that, then you measure, right, the amount of cubes or squares, the space around each city. So the second measurement you need to take is the space around each city. And those are the only 2 things you need to solve this problem in polynomial time. Once you have the distance along each dimensional vector to the nearest city along that dimension, and then you measure the space, right? The 8 outputs of space, 8 cubic spaces. Once you measure the volume or the area, depending on whether it's 3-dimensional or 2-dimensional, of space around each city, then you have the only 2 things you need to solve this. The thing is, sometimes the most important attribute is the distance, and sometimes it's the space, right? And the way you differentiate between them is the third, okay? If the distance is greater, you use the distance modifier first and the space modifier second. If there's more space than distance, then you use the space modifier first and the distance modifier second. So this third is what we call axis deviation. And it decides which one of these becomes more important on each particular city. Okay? So if you have a grid with a bunch of cities and you get these, first you measure the dimensional distance vectors. Dimensional vectors, you measure the distance along each dimensional vector. Then you measure the space. Once you have done that, you measure the deviation, axis deviation. That's all you need to create an algorithm that applies itself to each city independently. And with that, You then rank your cities and just put a line between the ranks. That's it. It's self-evident once you get that far. I will make a video just on the traveling salesman problem and how to solve it. But I am telling you, it's easily solvable in polynomial time if you use the orbital field. If you use dimensional vectors, 6-dimensional vectors, 8 quadrants of space, and 3 transitional planes. It is the same solution with these, right? This is your distance between each city. This is the volume or area of space around each city. And this is the axis deviation along any of the lines. That's it. This is the same solution that I use to solve the traveling salesman problem as I use to solve orbital fields, which is the wave function. It's the same model I use, orbital fields, to solve physics, quantum gravity, how anipoles invert to cause charge and mass on a particle, creating charged dipoles like planets, some atoms like carbon, protons, how baryonic matter, quantum gravity, how baryonic matter comes from dark matter, how it forms. There is just this orbital field answers dimensional vectors, 8 quadrants of space, 3 transitional planes, answers every possible question that you can throw at it. This is what makes it NP complete. This is how it physically answers the wave function. This is how it can solve any NP hard problem. You just have to interpret it. And this is the hard part. The hard part is you start with a new problem and you start having to just tear it apart. Well, what would be the distance? What would be the cubic spaces? The quadrants of space. What would be the transitional planes? How many transitions are there? Is it internal, external? Do the forces move in or out? Right? And once you find even one connection, then the rest unfold. The hard part for me, at least, is finding that one connection. Once I have it, I can solve any problem that is NP hard, whether it's about physics or computer science. How do I know, how can I solve quantum computing? How can I tell you it's ternary hardware instead of binary hardware, which is qubits, or unitary hardware, which is it's all within the orbital field. It's all within the wave function. It is NP complete.